You can answer that.
What's the S diagram?
Thank you. So Sherry asked, what's the S diagram, right? The S diagram is named after somebody named S, and it's this, okay? Where is it? What happened to the S diagram? Oh, here. It's named after George Santayana, who's a famous historian from Harvard, who said the following thing: those who cannot remember the past are condemned to repeat it. All right? So what does this have to do with a scientific diagram? It's because science has a history, and we should not forget that history if we want to solve problems. Otherwise, we're condemned to repeat the mistakes of the past. So here's an S diagram. On the bottom horizontal line, we've plotted the number of joules in a liter of fuel or of whatever energy source one would like to use. So this is a typical astronomy diagram because the interesting thing here is the quantity on the bottom. The more that you need to pack, the less compact is the equipment. So compactness of the equipment is over here. So it's good to have compact equipment because it costs less, so you want to be over to the right. On the vertical axis, we have the number of joules in a kilogram of that material. And again, the mass is on the bottom. So this is a duration of use. How long can you use a kilogram of stuff because you just has more energy? And you can plot all the usual suspects on this diagram. For example, wind. How much wind do you have in a liter of air that's moving at 7 meters per second? Okay, it's that less than 1 joule per liter. Okay, less than, much less, almost 10 to the minus 2. And this is the amount per kilogram, okay? But the kilogram is many liters of air. And here is uranium, okay? It's larger than wind on a windy day by 16 orders of magnitude in compactness of the fuel, and about more than 12 orders of magnitude in terms of the duration of the use. Right? And here is where hydro is, hydroelectric, because water 800 times more dense than air. You can make it fall over 100 meters, and it reaches much larger speeds than 7 meters per second. So when you calculate this, that's where hydro is. Here's where a supercapacitor is. Here's where a lead acid battery is. Here's where a nickel cadmium. That's what's in your cell phone. This is what's in your computer. This is wood. Much better than this. Better than any of this. Which is worse than bituminous coal. It's not as good as gasoline, which is not as good as methane, which is natural gas, if you were to compress it and cool it. Okay, so the methane in the US, this is in this state, it has much more per not much more than gasoline per kilogram, but much less per liter because it's gas. And if you want to ship it in Taiwan, you're not going to ship that big tank of gas. You're going to compress it and freeze it to cryogenic temperatures. So by the time it comes to Taiwan, it's 5 times the cost in the United States. So it might be a thing that the U.S. can contemplate, but not in Taiwan. Everybody talks about hydrogen. Hydrogen is great, so well above this in kilograms, but in liters, it's worse than methane. Say, well, why don't we store it in something? And hydrogen is notoriously hard to store. It's a very small molecule. It can go through metal. And you wait long enough. You have a hydrogen balloon, right? It quickly deflates. Right? So it's not easy. What's the best thing to do with hydrogen? The best thing to do with hydrogen is to combine it with carbon. That's what nature did for us, to make new things. That's why these things are so valuable. Here's uranium. So what's the paradox in this? The paradox is everybody says we can make do with stuff that's down here more cheaply than we can do any of this stuff. Is that true? How can this be? If it suffers so badly, right? That's a paradox. And they're roughly right, within a factor of a few. Wind and solar panels. I didn't plot solar panels here because they're kind of a two-dimensional object, okay? But if you really make them three-dimensional, they're like any electromechanical device. You can basically see that electricity has the same kind of order of merit as kinetic energy, but that means it's much worse than, electricity by itself has as much as stuff up here, okay? But the mechanical part is what brings it down. Anyway, so it would be roughly somewhere here. So how can wind claim to be as cheap as a coal-fired power plant or a gas-fired power plant, and that's cheap or cheaper than nuclear energy? You know, it's a paradox. How can this be? The things differ by this order of magnitude. How can they work out so that within a factor of a few, they're roughly the same? And the answer is exactly in that diagram. Because the way we generate electricity today is by turbines. So we have to burn something which causes something to flow, basically a wind of some kind of gas, which blows past a turbine, which turns past the magnet, and you get electricity. Well, a wind turbine is all turbine. Everything else, the turbine is much bigger than the reactor. So it doesn't matter what the reactor is. All your expenses are in building the turbine. That's how come this paradox comes to the same answer. Okay, because you're all basically eventually using in turbine electricity mechanical energy. Now, so these windmills are basically almost all turbine. How big are these turbines today to make them comparable in expense? They're roughly 150 meters tall. That's 50 some stories high. That's half of Type A 101. That's what people want to put up all over the place. All right? Well, maybe they're intermittent. So when they say the cost is the same, what they really mean is the nameplate power. When it turns at maximum, how much watts does it turn compared to a coal-fired power plant? And roughly, they're the same price. But it's not on all the time. It's intermittent. So that's kind of, not honest. If you really talk about saving carbon dioxide, you have to talk about energy, not power. Energy is power times the amount of time that you can use it. Well, wind, land-based stuff is maybe only 30%. Nuclear power plant is on 90% of the time. So there's a factor of 3 difference still. Okay? Moreover, when it's intermittent, you have to back it up. Namely, the grid will go down if you're counting on it to be there, and suddenly the wind stops. So the backup today is all done by gas-fired power plants or coal-fired power plants. The reason you can't use nuclear power plants is because of the problem with xenon-135. But in molten salt reactors, you wouldn't have that problem because you're always cleaning them of that xenon-135. So that hampers the light water reactors, but doesn't apply to. But anyway, today what's happening is when the wind or sun is providing enough, still these power plants have to come on in a second's notice. So they're constantly spinning. It's called spinning reserves. All right? And that's not counted against renewables. You're just burning it, not making any amount of electricity, just so that you can come on when the wind or the solar comes on. So you really need to make wind and solar better, and that's why I suggested, using that electricity when you can't use it to make chemicals. So although nuclear fuel is incredibly energy dense, right? The reactor doesn't much matter. So I can have this thing this size. So what if the turbine is the size of Type A 101, right? The cost is not in the thing that we can hold in this room. It's that thing that you built that's as big as Type A 101, not quite that big for a nuclear power plant, but it has so much baggage that it's become expensive. Moreover, you cannot make the core arbitrarily powerful because you got to get the energy out. As I said, thermohydraulics limits the core to a certain power density, and it's typically 100 kilowatts per liter. All right? Now, a kilowatt is about 0.7 horsepower. Sorry. Said the other way around. 1 horsepower is 0.7 kilowatts. So it's about 140 horsepower per liter. If any of you ever looked inside your car, you will know that you probably drive a car with that amount of horsepower, and the engine displacement is about a liter, okay, and the pistons and everything. And that's not a coincidence, that's just what you can do with today's material to get the power out. So nuclear, cannot be much better than this stuff, and this stuff doesn't have the baggage that's associated with it. That's how come today nuclear is inferior. But however, notice that this kind of power, 100 kilowatts per liter, is substantially more than a battery. Let's check that. Suppose we have a lithium-ion battery. It can hold roughly 10 to the 6 joules per liter. Can you discharge that battery in 10 seconds? No. If you tried, it'd burn, right? That's why battery cars are so expensive, because you need lots of them to get the same amount of horsepower. You can't just scale up this thing to one big thing. So you can ask yourself, is it reasonable that we can just count on stuff down here, plus maybe battery storage, so we don't need backup from these kind of batteries to replace the spinning reserves? And I would claim it's not possible unless you give them a lot of help. So let me give you that example. So here, everybody thinks we're going to, get rid of cars. Let's all drive electrical vehicles. Okay? So, what are the facts? So, suppose you have a puny little car, not a nice Tesla, something small, 21 horsepower. Well, an electrical motor is more efficient than a gasoline motor, so it's not as bad as it sounds. That's 16 kilowatt electric. That lithium-ion battery needs 50 kilograms of lithium carbonate. Okay, it's a fact. Each battery you can use for about 1,000 to 2,000 charge discharge, so 5 to 10 years. If you take your notebook and you charge and discharge it every single day, after a few years you need to replace that battery. Okay, that's it, 1,000 to 2,000. So that's 5 to 10 years, okay? People don't drive every day, roughly 5 to 10 years. So if you divide that into here, you see that you need 10 to 5 kilograms per year of lithium carbonate. So where does this lithium carbonate mine? It's mined. 27% of it is in the Atacama Desert. Does that sound familiar? What does A stand for in Alma? Right? When we really get desperate and need batteries, if we go this way, you can be sure they're going to be up there mining that stuff. Are we still going to be able to do astronomy in Alma when this happens? To displace one gas diesel car, okay? 10 to 5 kilograms per year. The total world lithium carbonate production is 100 million kilograms per year. So you divide this by that. You divide this into that, you see that EVs can displace 10 to 20 million cars. That's a lot of cars. How many cars are there in the world? The world has 1,000 million cars, 1 billion cars, to grow to 2,000 million cars in 2050. So even if you say, look, let's not use lithium for anything other than to run cars, EV at best is 1% of the petroleum that's burned in cars, okay? Which itself is a 10% emitter. So even if you devoted all the lithium production in the world, okay, you've solved 1/10 of 1% of the problem. Is that enough? What's the answer? Well, the solution can't be, dig deeper. Must be, we need to recycle, reduce the cost of... Batteries are not recycled today, okay? You can think it's recycled. They're not recycling the lithium carbonate. That's too expensive, so they build you a new one. Well, we've got to stop doing that. We've got to recycle it. So if you want to recycle it, and I've been thinking about doing this,